calling it and returning from it. When we embed the PL SQL inside of SQL, it's compiled a little bit differently so that the call overhead is significantly reduced. And that's where the CPU savings came from. Number 2 is another sort of developer feature, improved defaults. You can now default a column to a sequence number. So instead of having to write a trigger that assigns sequence.nextVal to your primary key or something like that, you can just default it. We can default when a null is inserted into a column. I'll demonstrate that so it's a little bit more understandable. There is an identity type, which depends on this new capability. The identity type automatically generates a sequence and auto-populates that column. This is primarily for migrations from other databases that support the same identity type concept. And then the last one is sort of a DBA feature, metadata only defaults. And I'm going to demonstrate that one so that you can understand what it is as well. But defaulting to a sequence is pretty straightforward. You just can now say default sequence.nextVal. And as you would think, you just leave that column out of the insert statement and it will default it for you. You can also default on null. With default values in the past, you could say that a column had a default. And if you wanted to insert a row into that table that used that default, you would either have to leave that column out of the insert. So column Z, for example, to get the default in the past, would have to be left out of the insert, not referenced at all, or if it was in the insert, you would have to use the keyword default in the values list. So if at a point in your code you sometimes wanted the default and sometimes did not, you would need 2 separate inserts, one that allowed the default to go in and one that would put in an explicit value. If you had 2 columns with defaults, you would need at least 4 inserts to handle all the cases and so on. So it was a bit cumbersome. With this default on null, this is saying that Z is now a not null column. If you attempt to insert null into it, we will default it to 42 in this case. So for example, here I insert explicitly Z and I set a null value. It's defaulted to 42 for me. So now I would only need 1 insert. I could bind a null when I wanted to, and it would have the default, or I could bind an explicit value. The identity type, this is simply a shortcut for creating a sequence and defaulting this column to a sequence. It also has the nice attribute that when this does generate that sequence for us, it attaches it to that table so that if you were to ever drop that table, the sequence would disappear as well. So this is generated as an identity. If I attempt to insert into that column, it will fail because I said it's always generated as an identity. So what I would do is insert without that column, and it will pick it up from this new sequence it created. Since it is a sequence under the covers, you can use all of the sequence parameters. I can have my start with and increment bys, but I can also use this syntax generated by default. This would allow me, if I want to explicitly specify a value for that column, and it will take it. Or if I leave that column out of the insert, it will default it to this newly generated identity. And then the last one is sort of for the DBAs in the room. If you've ever altered a table and added a column with a default value, you've probably noticed that it can take a really long time. Because in version 10 and before, what happened was we would lock the table, add the column, and then update every single row in the table, and then commit. And so that would be a very long blocking operation. In version 11, if you altered a table and added a column with a default value and specified that column is not null, we would do what was known as a fast add column. We would lock the table, add the metadata for the column, and remember the default value in the data dictionary, and then commit. We wouldn't update as long as that column was not null. Because what we would do at runtime, when we retrieve that row, if the column value was actually missing, we would just return the default value. So we didn't have to update everything. But if you tried to add a column to a table that had a default, but also supported nulls, we would have to go back to the old slow way of doing it. Lock it, add it, update every single row. Starting in version 12, this is no longer true. And so to demonstrate this, I'm going to copy all objects. It's taking about 12 megabytes right now. I'll go ahead and add a very large column, a char 2000, with the default of X. So that's adding 2,000 bytes to every single row. And in version 12, that happens instantaneously. In version 11G and before, this would be a long-running operation, because that actually updated every row in the table. And you can see this if we measure the space. It's still 12 megabytes even after I added that column. But in 11G, the table went from 9 to 192 megabytes. Okay, so this allows you now to add a column to a table instantaneously in an almost online fashion. Number 3, some increased size limits for varchars and raws. It was way back in version 7.3 to 8.0 was the last time we increased the size of a varchar. In version 12, these can now go to 32K in size. You do have to enable this. It's not enabled by default, so the DBA would have to set an init.aura parameter, and they would also have to run a small upgrade script while the database is open in exclusive mode to upgrade the data dictionary. And this is a one-way road. If you enable this capability in your database, this capability will be enabled forever. There's no way to back out of this. So do make sure you want to do this prior to doing it. All the Oracle tools like Application Express and SQL Developer and SQL Plus and so on are expecting 32K strings, but some other applications, other tools may not be quite ready for it, and that's one reason for not enabling it by default. Easy top-end and pagination queries. This has got to be one of the most frequently asked questions in my career of taking questions and answering them. And the question is, how do I get the first n records from a cursor? How can I get rows 21 through 30 from a result set? This has always been doable, at least since Oracle 8i and above, using row num or row underscore number, an analytic function. It was always doable, but it wasn't easy or clear. It was a trick that generation after generation of programmer would hand down to the next generation. And it was also a little bit error prone. If you didn't put the parentheses in the right place and put the where clause against row num in the wrong place, you would get erroneous results. With this pagination, this becomes pretty easy. There's a new clause that will go at the very bottom of the query after anything, including the order by, and you can say fetch first or fetch next number of rows, and you can also use an offset clause. So you could say skip 20 records, give me the next 10 records, and that would give you rows 21 through 30. So here's a quick look at the syntax. I'll copy all objects again, index the owner and the object name. If I run a query that selects some things from the table, order by owner object name, fetch first 5 rows only, it will use the index to find those first 5 records, return them immediately without having to sort the entire thing. Down here in the filter, in the predicate section, you can see that it's really just rewriting our query to use the built-in analytics. So this is not necessarily providing any new functionality. It just makes it syntactically much easier. Also, it's a little bit more portable. Other databases have this offset and fetch clause. And here's an example of the offset. I can say skip 5 rows, fetch the next 5 rows. You can also go for a percentage. So I can say run this query and give me the first 0.01% of the result set. Now notice in this case, as opposed to the previous ones, these were using an index to get the first rows as fast as possible. If we're asking for the first n% of a result set, the first thing we need to know is how big the entire result set is. So in this case, it's going to have to read and process all the data so it can figure out how big the result set is to give you the first 1%. This would be good in a warehouse reporting sampling situation. Most of the times you're going to use this in an OLTP type application, give you instant access to the first rows. This will have to build the entire result set, but then let you sample it, get the top 1%, top 10%. The next one is a change to the SQL language, a pretty big one. If you go way back in time to, like, say, version 7, SQL would let you take multiple tables, join them together, and then you could have a where clause that would simply look left and right in the result set. You had access to the row, and you could compare column A to column B. Then came along Oracle 8i, and we introduced analytic functions like lag and lead, first value, last value. And these allowed a result set to not only look left and right in the where clause, but now up and down. I could look back a row. I could look forward a row. And this was pretty powerful, right? It gave us the ability not just to look at a single row at a time, but a whole set of rows. But there was still a class of questions we couldn't answer easily using these analytics. Like, I want to find a pattern in my data. For example, I might be analyzing stock information, and I'd like to look at all of the stock prices for a stock over time and look for a pattern in that. I'd like to see that the stock started at a high price, started declining, hit a low price, and then started increasing. So I want to find a V-shape in my data. Lag and lead, the analytic functions, wouldn't let you do this very easily because you had to know exactly how many rows you wanted to look backwards or forwards. And for some stock price, the V might take 10 days to go to the bottom. For another stock, it might take 100 days. You don't know how far you needed to look backwards and forwards. So we needed to be able to pattern match against this. And that's what this new clause, match recognize, allows us to do in SQL. In a single pass against the data, we'll be able to look for a pattern in it. To demonstrate this, I'm going to use that stock example. So we'll have a stock symbol like Oracle, a timestamp, which is just a date, and then the stock price. I'll populate some data in there, and then using SQL Plus, we can visualize this information very easily, right? And we can obviously see these V-shaped patterns. For 13 rows of data, SQL Plus would be phenomenal. For 13 billion rows of data, this isn't going to work very well, right? There's just too much information to display graphically on the screen. What I'd really like to have is a result set that would just give me 2 rows for these 13 rows. One of the rows would tell me the stock started at a high price on this date, it bottomed out here, and then it had this as the next high date. The second row would simply be another observation that this was a high price that went down to this low price that finished off at this high price. So I want 2 records. I actually want this row here for 7th of September to be output twice because it's going to be the last point in one of the V-shaped patterns, but it will also be the first point in the second V-shaped pattern. This is the SQL syntax I can use to do this now. So we'll walk through this line by line, basically. Up here, I can have any query. I generate a set of data. So I'm just doing select star from stocks. Lines 3 through 15 are the match recognize clause. I start by breaking the data up into sets, just like I would with an analytic function. And here, I'm partitioning the data by the stock symbol. So if I had Oracle and Microsoft and IBM, I would analyze each of those 3 stocks separately and apart from each other. Within each stock symbol, I'm going to sort the data by timestamp. So now this SQL statement has an ordered stream of information coming into it. Against this ordered stream of information, I'm going to skip down a little bit. I want to look for a pattern. And this is the real heart of the match recognize clause. The pattern I want to look for is I want to find a starting record followed by a down record. And since there's a plus there, this is like a regular expression. That means I would really want to find 1 or more down records. That is then followed by 1 or more up records. So basically, in regular expression talk, I want to find any record followed by 1 or more downs, followed by 1 or more ups. That's my pattern. Now I have to define what these things in my pattern mean. So we go to the define section. I don't have a definition for start. That means start is always true. That means start can match any record in my result set. I then have down in my pattern. Down is defined as my row's price is less than the previous row's price. That's simply what it means to be part of this down pattern. And then I have the definition for up. Up is my row's price is greater than the previous row's price. Now we're ready to start interpreting the SQL statement. We'll get back to the rest of the syntax in a minute, but we've got our pattern, we've got our ordered stream of information here, and we want to apply this pattern to it. So we get the first record. That matches the definition of start, because start matches any record. We continue on to the second record. In order for this to match our pattern, it has to be a down record, because start has to be followed by down. In this case, the stock price was less than the previous row's price, so it matches our pattern. If, on the other hand, this stock price had been equal to or greater than the previous row's price, that first record wouldn't have matched our pattern anymore. We would reject it, and we would have restarted the pattern matching on the second row. But in this case, the second row matched our pattern, so we continue on. We get to the third record, and according to our pattern, it either has to be a down record or an up record. We look at it, it's still a down record. We continue on to the fourth record. It's no longer a down, but it does match the up. We have just matched our pattern. Right? We found any record followed by one or more downs, followed by one or more ups. But just like a regular expression, we're going to try to match the maximum pattern. So we're not going to stop there. We're going to continue on to the fifth, the sixth, and the seventh record. They're all going to match our up pattern. We get to the eighth record, it doesn't match the up pattern anymore. So we have found the largest set of records in the stream of data that matches the pattern we've been looking for. Now we need to figure out what to do with it. Back to the SQL statement. On line 9, I said one row per match. This match recognize can either work like an analytic function, meaning it would return all of the rows in the pattern. That would be one option. Or it can work like an aggregate. It can return one row per the match. And that's what I wanted to do here. I wanted to take these 7 records, get some information from them, and just output one record. The information I wanted is up here in the measures section. I wanted my starting timestamp, I wanted my last down timestamp, and my last up timestamp. There's many other built-in functions and attributes, measures that I can put here. This is a relatively simple example. So I get these 3 attributes, and they're right here. The 1st of September, 3rd of September, and the 7th of September. So I'm getting to see the stock symbol, and the beginning of the V, the bottom of the V, and the ending of the V. That's exactly what I wanted. Now I need to figure out where I want to start looking for the next pattern in my data. Obvious choices would be start on record number 2. I could start here. But that would be very repetitive in this data set, because I would find V's inside of V's inside of V's. So what I wanted to do was actually start on the last record of the previous pattern. And that's what I said here. After match, skip to the last up. Up is my definition of up, and it would start the next pattern match here, and it would go through and find this V, and then output this record. So notice in this result set, the 7th of September appears twice. Effectively, this record appears twice in the output. I would like you to think for a minute how hard, how impossibly hard this would be to do in SQL in version 11G. I've tried to do it. It can be done. It is really, really hard. It took many more hours to think of how to do it in 11G than to put together this entire presentation. Okay? And once you do get the query, you're going to find that it's so complicated, so many self-joins, scalar subqueries, analytic functions, sorts going on, that it does not perform very well at all. This query, in a single full scan of this table, can find this pattern of data. Doing it in regular SQL would have required multiple scans, multiple self-joins, a lot of temp space. It's not feasible to perform in regular SQL. So this allows me to do something inside of SQL that I really could not have done in prior releases. You might look at this and say, this looks like big data. analytics. This looks like something people would take a whole bunch of data out of the database, throw it into a Hadoop distributed file system, and write Java code against. I'll throw 1,000 CPUs at this. This is something that prior to this match recognize, you would probably have to use a big data solution against. You'd have to take it out of the database and throw hundreds or thousands of CPUs at it in order to do this in a reasonable amount of time. This is now something we can do inside the database without having to unload it into another database and use different approaches against it. Number 6, some partitioning improvements. This is predominantly for DBAs. Global indexes. If you're using partitioning, you understand that there's 2 types of indexes, local and global. When I perform partition maintenance operations, like adding or truncating or dropping an existing partition, my local indexes would be fine because there was a one-to-one relationship between an index partition and a table partition. Drop an old partition, drop the old index partition. It would be okay. But then there were these global indexes. Global indexes are indexes that are partitioned using a different scheme than the table. There's not a one-to-one relationship. And if I dropped an old partition, my global indexes would either go invalid and need to be rebuilt, meaning that drop partition becomes an offline operation, or the drop partition would have to maintain the index, meaning the drop partition, instead of happening in a fraction of a second, might take hours or days to complete. With asynchronous global index maintenance, we can now drop an old partition, have the global index stay valid, but not have to remove those index entries right away in the foreground. The queries that hit that global index would just ignore any row ID that pointed to that dropped or truncated partition. So they operate a lot like a deleted leaf row would in an index. And that index would be maintained asynchronously in the background. So it would not affect the DDL operation. It would not affect the availability of the data. We also have cascade functionalities for truncate and exchange. If you have parent-child relationships, like in orders and a line items table, you can now do a cascade operation on a truncate or a drop so that when you truncate the oldest order partition, that truncate cascades down to the child tables for you automatically. So one DDL statement can affect multiple tables segments now. Same with exchange. If I'm going to load a parent-child table, I can now exchange both of those tables or 3 of those tables or however many tables are in that relationship into my partition set of tables in one DDL statement. We also have multiple partition operations in a single DDL. If, for example, you had a very large partition that you wanted to split into 4 partitions, the DBA would have to execute 3 DDL commands. One would take the initial large partition and split it into 2. The next one would take one of those 2 and split it into 2. And then the next one would take one of those 2 and split it again. It would have to read and reread that data a lot in order to perform these operations. With this multiple partition operations, I can do this in one statement. I can split a partition into 4, or I can take 4 partitions and merge it into 1. We also have an online move of a partition and the ability to use interval and reference partitioning together. They were exclusive operations in version 11, those 2 partitioning schemes. They can now be used simultaneously. Number 7, adaptive execution plans. This is the ability of a query plan to change its mind as the query is progressing. You know, the optimizer works by guessing at how many rows are going to flow through each step in an execution plan and says, I think I'm going to get 2 rows here, so I'll use an index, and I think I'll get 2 more rows over here, so I'll use a nested loops join. If those numbers are wrong, if instead of getting 2 rows, it gets 2 million rows, the subsequent steps in an execution plan may be incorrect. If we got 2 records out of that index, nested loops made sense. If we get 2 million, nested loops do not make sense. I probably want to use a hash join. This adaptive execution plan allows a query plan to change like that. So for example, I'm going to create 4 tables. They all have the same exact data, copies of all objects. I'm going to index the object ID in here. We'll gather stats on this, and then we'll do something really mean. We'll update the information. So the statistics were gathered before this update happened. As far as the optimizer is concerned, every object ID in that table appears twice. However, we've come in and done some updates so that thousands of rows have an object ID of 42. I've introduced some skew into the data. But the optimizer is not going to know that because we've already gathered statistics here. 2 rows giving me 4. I'm going to join that to 2 rows, 8. Join that to 2 rows, about 15 or 16. And so it comes up with a query plan that uses all int 42. The optimizer said, okay, about 2, got way more than 2. Nested loop is a bad idea. I'm going to stop using indexes and start full scanning and hash joining. Now, out of this join step, I was expecting 4. If I would have gotten close to 4, I would have continued on with the original plan, but here I didn't. I got 3,484, so I'm going to stop using indexes again and do the full scan. The query plan adapted. This is what we thought would happen. This is what actually happened. You do have the ability to see the entire plan. Okay, so this is coming out of the trace file. The entire plan was, we think we're going to get 2 records out of this step. We're going to feed that into this new step called a statistics collector. It's going to count the rows that have actually come out of the earlier step. If the number of rows coming out of the earlier step is close to what we predicted, we're going to use nested loops. Otherwise, we could use a hash join. So inside of this one query plan, there's actually many different possible query plans. And depending on the number of rows flowing from step to step, the optimizer will pick and choose the right next step. The query plan can adapt as short. Number 8, some enhanced statistics. We have the ability to gather statistics during data loads. So since version 10, every time you create or rebuild an index, we've already computed statistics on it. Starting with version 12, every time you load an empty segment using direct path operations, we'll gather statistics on it. So here I just did a create table as select, and I turn around and I can see that the table's already been analyzed. We also have the ability to have session private statistics on global temporary tables. Global temporary tables and statistics were a hard thing to figure out. You know, if some programs used 5 rows in the global temporary table and some programs used 5 million rows, it was hard to manage those statistics. This new capability allows each session to have their own set of private statistics. So here I've logged in, I've inserted 5 rows, no stats on the table, gather stats. It now thinks there's 5 rows. The optimizer uses 5 to come up with a query plan for this one. It's telling me that we were using these global temporary table session private statistics. If I create a new session and I just start using that global temporary table, I can see it has no statistics. The DBMS stats I ran in the other session is not visible to this session. And now I get a completely different query plan because the optimizer, using dynamic sampling in this case, filled in the missing statistics for me. So I got the right plan in each session. Another way to do it would be to use set table stats. If the developer put the rows into the table, they know how many rows there are. So here, I told it, there are about 300 rows. Number 9, temporary undo. If you've used global temporary tables, you know that they actually seem to generate redo, even though they write into temp. Right? So I'm doing all my inserts, updates, and deletes in temp. Some redo has been generated. The redo that was generated was for the undo that was generated by those operations. In version 12, we can have the undo for global temporary tables go into the temporary table space. That means that inserts, updates, and deletes on your global temporary tables will generate 0 bytes of redo. Another side effect of this is in an active data guard environment, we'll be able to do inserts, updates, and deletes on global temporary tables, since they'll no longer write to anything but the temp table space. So you'll actually be able to do some modifications in a read-only database with this. Data optimization. the database now has the ability, all the way down to the block level or the segment level, to watch and track the temperature of your data. It will remember what parts of your table are hot or active, being recently read and written to, what parts are warm. You're still reading a lot of this, but you're not writing it very much, and which ones are dormant. I'm neither reading nor writing this, but I need to keep this data online in case somebody wants to access it. Based on the temperature of the data, you can use declarative DDL to set up a policy that tells us how to manage it. Hey, this orders table, when a partition has not really been utilized in a long time, it hasn't been written to, I'd like you to magically move this partition for me and compress it. Or when this data goes dormant, it's not being read or written to very much, I'd like you to take this data and move it from this table space to this other table space, perhaps from expensive storage into cheaper storage. But this is all done declaratively now. And then the last two, SQL text expansion. Have you ever been given a really simple query, select star from table where column equals some value, and been told it's running really, really, really slow. It takes like an hour. And you ask for the explain plan or something like that, and you get 15 pages of information, right? You know that the very simple query you received is actually a query against a view now. And it's probably a query against a view of a view of a view that joins 15 views together and unions a couple more. You'd like to see the expanded text. This becomes really easy to do in this release. You just give us the original SQL text, and we will output the expanded text, whatever the actual query being optimized was. This also works with a feature of the database called Virtual Private Database. So with this feature, I can write what we call a predicate policy function. It returns a where clause. I can then take a table and using fine-grained access control, associate that predicate policy function with the table. So when somebody queries this table, this where clause will silently be added to it. Well, these where clauses can be